Hi there. Welcome to Latent I/O. Today we're working out what it actually takes to run a good AI model on your own machine. Almost everyone starts by asking whether their graphics card is fast enough, and that is the wrong question. To produce a single token, the machine reads every weight in the model out of memory, not some clever subset, all of them every time. So the arithmetic units mostly sit waiting, and the pipe between memory and compute does the real work. Two numbers decide what you can run and how it feels, how much fast memory you have, and how fast that memory is. The first number is capacity, and it is one multiplication. Multiply the parameter count by the bytes each weight is stored in, and that is roughly the memory the model needs. At full precision, a weight costs 2 bytes, so a 30 billion parameter model wants 60 gigabytes, more than any consumer card holds. Quantize down to 8 bits and a weight costs 1 byte, and at 4 bits it costs about half of one. That same model now lands near 17 gigabytes, which fits on hardware you might actually own. Then leave headroom, because the context window lives in memory too, and grows with everything you paste in. The second number is bandwidth, and it is the one people skip. The whole model has to move for every token, so tokens per second is roughly bandwidth divided by model size, and you get about 2/3 of that in practice. So take our 17 gigabyte model to 4 different machines. A high-end graphics card moves around 1,800 gigabytes a second, which works out near 70 tokens a second. A laptop-class unified memory chip moves about 550, so you are looking at roughly 20. A large unified memory mini PC moves about 250, and you land near 10. Ordinary desktop system memory moves about 90, which leaves you around 3 tokens a second. Comfortable reading is about 7 tokens a second, so that last machine is not slow, it is unusable. That first number matters more than it looks, because fitting is not a preference, it is a cliff. If your model is one layer too big for the fast pool, that layer gets pushed into ordinary system memory. And every token from then on waits for the slowest link in the chain. You do not lose 10%, you lose an order of magnitude, because part of your model is now being read at 90 gigabytes a second, instead of 1,800. It is the story people tell constantly. It ran beautifully, I went up one size, and it fell off a table. Seen as capacity and bandwidth, the hardware market collapses into one trade-off with 3 answers. A discrete graphics card is a small pool of very fast memory, blistering on anything that fits and useless on anything that does not. A unified memory machine, like an Apple desktop or a mini PC with soldered memory, is a big pool at middling speed. It runs models the card cannot hold, at maybe a third of the pace. And an ordinary PC on system memory is an enormous pool at a speed that is technically correct rather than usable. Nothing at consumer prices gives you both, so the real question is which side of that trade you need. One model design bends the formula in your favor, and it is why the strongest local models look the way they do. A mixture of experts model splits its weights into many small groups and activates only a few per token. All the weights still have to be resident, so the capacity number does not move. But only the active slice gets read on each pass, so the speed number behaves as though the model were much smaller. 35 billion parameters with 3 billion active costs, you 35 billion worth of room, at close to 3 billion worth of speed. That is the one case where the division underestimates you. Which leaves software, and it takes up far more of the conversation than it has earned. One inference engine does the real work underneath most local setups, and the friendly tools you have heard of are wrappers around it. One is a command line, another is a desktop app with a chat window, and both hand the same files to the same engine. Nearly all of them expose an open AI-compatible endpoint on localhost, So code you wrote against a hosted model works once you change the base URL. Picking one of them is an afternoon. Picking your memory is the decision. So you never need a benchmark to answer this again. Multiply the parameter count by the bytes per weight to see whether it fits, and leave room for context. Then divide your bandwidth by that size to see how fast it runs, and keep about 2/3 of the answer. Fit comes first, because missing it costs you a factor of 20. Speed comes second, because it is the difference between a tool and a party trick. If you want more AI concepts taken apart like this, subscribe and turn on notifications. See you in the next one.